Cool. Thanks. Welcome everybody here. Thanks for coming. So, unlike Herbert, it's not my birthday today. But I did officially turn this year years old. So I've been hacking stuff now for about 25 years. So I've been thinking a lot about, how can we get rid of classes of issues in terms of security instead of just poking holes in new things. So one of the things that I've been working on more recently is what we like to call pre-silicon fault injection, which is actually doing fault injection before the silicon exists, so before the chip has actually been made. Because if you can figure out at that point what your vulnerabilities are, you still are in a place where you can fix them. So the way to do that is to do simulations of the chip and also simulations of the fault, and then investigate what the effects are and see if you can actually come up with some countermeasures. So let's try to get into that. So first, for the we've heard the term fault injection a couple times already today. I just want to give you just a quick overview of kinds or types of faults that you could inject. I'm going to start really with the basics. So this is, in the top right, what you actually see is part of a barbecue lighter. And as soon as you click it, you actually create a spark, which is normally used to light the gas inside of your barbecue. But if you're careful, you can also use it to change bits on a chip through the electromagnetic pulse that actually occurs when you do this. Do make sure that you put some of that Kapton tape over your device, because otherwise you're going to fry the whole thing. But this is like a $2 fault attack. If you want to spend a little bit more money, then you can get devices like a chip whisperer. And if you're, want to apply your kindergarten skills of gluing, you use that to attach the wires to your, they're soldering underneath there, but then you want to fix it with some glue. So you can use this for voltage blitzing. So, playing with the power supply onto a chip and injecting faults that way. If you want to get a little bit fancier, you can use things like BBI, stands for body biased injection, but basically what you're seeing there is a chip, and we're touching a needle on the substrate of the chip, which is, let's say, the ground plane of the chip. And if you play with the potential of the ground plane, you're actually also injecting faults in a chip as well. I think we have maybe not a demo setup, but we have some of these needles out there in our booth you can go and check out. They're sharp, don't pinch yourself. And then you can go even further. You can do things like laser fault injection, where you have this laser set up, and what it does, it shines a very bright beam of photons on a chip, which actually causes transistors to open up. Maybe transistors that shouldn't be open at a particular point in time, which means that you've also injected a fault. And if you want to get really precise, you can do things like this. I stole this actually from a paper from Sergey, which I think is also in the audience. But it's basically microprobing. So if you open up a chip, you can put these microprobes on the metal wires that are on the chip, and you can basically inject single bit faults. So, all very cool, very visual, but why am I bringing this up? So, really the mental model that we should be having when we're doing simulation as well is that we have some sort of physical disturbance, and this causes bits to flip inside a chip. That's really what all there is to it. And then, of course, we want to try to flip bits that have some sort of meaning with security. So, how are we going to simulate this? I'll first talk a little bit about how actually chips work, because we have some physical disturbances that we're doing. So let's just look at the physics of the chip, and then we'll see if we can go back to the logic level. So how does a chip work? These are some pictures of an actual chip on the top, basically different layers of the chip. And what you see in, well, let's start on the right-hand side, are basically the transistors. And if you add metal 1, you get things that are called standard cells. The standard cells are basically just, if you don't know what it is, think of it as like the OR gates and the AND gates and the XOR gates and the flip-flops and sort of those digital elements that, that a chip is made up out of. And then we need to connect these together to actually form a circuit, and that's what the other metal layers basically do. I'm waiting for Olivier to correct me. So far, so good? But this is the sort of the physical view of that. So when you design these things, you're actually not looking at this. You're maybe actually even looking at higher level design languages. But in the end, it's basically gates and wires. So we're going to use this as the logical view of what's actually happening on a chip. So now, what happens if we actually inject a fault here? So let's say we have a chip and we shoot a laser at it, or an EM pulse, or whatnot. There's various things that can happen. And it will really depend on the kind of fault injector that you're using, what's actually going to happen. So in the extreme case, let's say the microprobing example we had, we can actually pick a particular wire, and we can pick a particular time, and we can inject a single bit fault. That's about as precise as it can get. Now, if you think about the other examples, like the barbecue lighter, I have nowhere near that precision, right? I don't have precision in time, I don't have precision in space, and I will probably be corrupting a whole bunch of things on the chip. And I always think the magic of fault injection is that the chip will still usually work, and you can actually bypass security with these kind of things. But if you start thinking about it, it probably has to do with the fact that a lot of the chip is actually not relevant at a particular point in time. So you're just hitting it with a hammer until you accidentally flip the bits that do matter, and then you can continue. For the purpose of today's discussion, I'm going to just be talking about single bit flips, because they're a little bit easier to simulate, but you can ask me complex questions about this later if you want. So let's talk about simulation. So let's say that we have this particular circuit. So really what it is, I have two values, A1 and A2. I invert them. I take the OR of the two, I store them in a flip-flop, and out comes a value. Just a random circuit. It doesn't really matter, but that's how you represent it there. Now, if you write this in code to simulate it, it's basically a couple statements. So you take this wire 01, which is represented there, which is the inverse of A1. Same for 02, which is the inverse of A2. Then you take the OR of those two, and that eventually becomes flip-flop value X. Now, this we don't have to invent, luckily. There's a tool called Verilator, which basically takes a Verilog description of such a netlist and turns it into a C-code simulator. Now, it turns out that Verilator does this sort of like this. So it sees that it's a network. All these wires are just single bits. So to make this correct, it just basically puts an AND with 1, which masks off all the higher order bits off. But it stores everything as a byte still, for some reason. So now that we have that code, we can give it arbitrary values for A1 and A2, and out come the values for X, and we're all happy with our simulation. So how can we start injecting faults in this? So there's a few ways you can do this. We actually chose to do it at the Verilog level. So if you have some circuit, this is a little bit different one than I just showed before, but the concept is the same. We basically introduce a thing we call a glitch bus. And at glitch bus, we can, at arbitrary points in time, we can basically flip the output of arbitrary gates. So this gives us, well, I guess if I say infinite possibilities, somebody's going to correct me, because it's not infinite, but it's a lot of possibilities here for faults. So we have to make some choices, right? And like I mentioned before, for now, we're just going to make the choice to do a single bit fault, which means that on this glitch bus, I'm just going to have a single bit set to 1 at a particular point in time, and I'm going to put it to 0 all the rest of the time. So now the complexity is basically the number of gates I want to flip times the number of clock cycles that I want to try to do this. Which can be manageable, but it's still fairly slow. So one trick, at least, that we are exploiting in Verlader is the fact that it uses that and 1 there. So it's actually using only 1 bit out of out of a byte. So if you actually drop all those and 1s, what you're basically doing is you're simulating 8 circuits in parallel. So you can still write the same code, but now you can just use every bit in the byte to simulate. And you can do this for arbitrary widths. If you change byte into word or whatever your favorite integer size is, you can run that many machines in parallel. So this actually speeds things up quite a bit. One of the things we've seen is that the speed of this actually really depends on your iCache size, because this is very instruction heavy. So, I'm putting in an instruction for every gate. So if I have tens of thousands of gates or hundreds of thousands of gates, it's basically a very long list of these kind of equations without any loops or anything like that. So that really bogs down your iCache. So using these kind of optimizations really helps. Okay, so far so good. I see a thumbs up even. Awesome. So, demo. This is where I have to say something about what kind of sacrifices I did to make this demo work. Actually, I did none. It's my wife. She's at home with a 3- and a 6-year-old without me. So I wish her the best of luck. So let's see if we can, I will actually this back in here. I can use my demo fingers. Do I need to change the thing here? Is this real? I'll try to blow this up for you. What's the hotkey for making this bigger? Say that again. Control W? No. Control plus? No. Control Shift plus? Oh. Use the mouse. Okay. Better? I'm asking the people in the back, I guess. I get a thumbs up again. So, I said I was going to do a demo on a Fika RV2 core, so maybe I should explain what that is first. So, Fika RV2 is a RISC-V core. That's actually open source. The Verilog is available. It's written by Claire Wolf. And it's a very simple CPU, which basically takes RISC-V instructions and executes them. It doesn't deal with caches. It doesn't deal with parallelism. It's nice and small, and it's really great for sort of research purposes. So that's where we're sort of starting. And what I want to show is injecting a fault in a piece of code that RISC-V core actually executes. So the sort of interesting bits of the code are here. And really all it does is it prints something, basically branch test. Then it reads a single byte from a simulated UART. The simulated UART always says 0, which means that this if success condition will always return 0, which means it should always print failure. Now we're going to start fiddling with this glitch bus. We're going to start fiddling with basically all the internal state of this Pico core, and we're going to monitor whether it prints success. Because if it's print success, that means we've somehow successfully bypassed this branching condition. And this is a toy example, but you can imagine this is a password check or any kind of authentication check that you can bypass this way. So I want to maybe do a little poll of the audience. So we have this if success condition, right? And we have about, what is this? Like 15 lines of code with a couple of braces. In how many different ways do you think I can cause, with a single bit flip, this thing to print success? Any hands for 1 to 10? 20 to 50? A couple of hands. 50 to 100? 100 to 250? 250 to 100,000? Alyssa's going to win. All right. I was going to challenge you with something else, but now I forgot. You can do presenter notes when you're live doing a demo. Anyhow, let's see what happens. So I'll just start it. So this is just running the simulation. So it's actually running for 800 clock cycles. I timed the whole code, from start to finish at about 700 clock cycles, I think. And it's going over, can I see that here? No, I can't see that here yet. It's going over some number of flip-flops. So what I'm actually doing is even made the problem smaller already. So when I was talking earlier about flipping all the gates, actually I'm only flipping the flip-flops, which is where the tongue twister comes from, by the way. Because it's a little bit more manageable for this demo. So this takes on my laptop about 80 seconds or so. So I'm coming up with stuff to fill this void for you, so we're not just staring at each other. But after this 80 seconds, we'll see like how many different ways this code can actually be glitched. And it always blows my mind. It's almost done. This is sort of a in-between print, but see, you've seen it's already simulated about 1 million faults, of which we're already up to 514 different ways. It should be almost done. So there we go. I have to go up a little bit to go to the final number. So here, I don't know if you can see it, there's actually 519 different ways I can glitch this piece of code with like 13 lines to get it into success condition. And this kind of goes back to my earlier statement, like we're hitting this thing with a hammer, right? So we might not actually be doing single bit flips, but there's a lot of different ways we can get this thing to do what we want anyway. So this aligns with what we see in practice. But for me, what always blows my mind is like just how many different ways it's possible to do that. What I'm doing here is I'm printing the clock cycle at which point I get faults. So here you see clock cycle 423. There's actually 98 different ways of glitching it at that particular point in time, which is about 20% of the faults in total that we detected. So let's just have a look at that clock cycle. Actually, if you look down, it's 424, which is just after that. 422 is just around that. 421 is all around that 420-something clock cycle. So what happens there? Anybody wants a warrant to guess before I show the answer? It's the conditional branch, Jasper. Yes, it is. Oh yeah, this was just I haven't done this, but this is just to show you a trace of what happens if you inject one of the faulty ones. It actually does end up printing success, which is what you would expect. This is a chart of what I just showed. So you can see clock cycle 423, 424, 422, 421, 418. They're all sort of clustered around a particular area. And you see there's just a ton of ways that you can glitch it. Which is good news, because maybe that means that we can apply a really local fix to actually get a lot of these faults out of our system. And yes, you guessed correctly. So around clock cycle 423, well, we're simulating a core, so we know exactly at what program counter it is. And because we also know the firmware, we can look in the firmware at, well, program counter was at hex 88. I can look at hex 88, and it's indeed at the, if success condition, this conditional branch here. So there's all kinds of way to get this conditional branch to flip the condition around. So let's see if we can actually fix it. So let's hope that my wife's sacrifices have been successful, because I'm live going to fix the code. That's going to be trouble. So I'm just doing a really dumb fix, which is basically to do the check twice. So I'm again going to read from the serial port. It's going to give me 0. So even if for some weird reason it has passed this success, then it needs to read it out again and pass the second time as well, and then print success. So let's save this and recompile and rerun it again. So we can place some more bets now. So now that it's actually compiled, we can place some more bets now. How many faults are we going to go down to now? 100? Less than 100? Get some hands. Less than 100? 100 and between 100 and 200? 200 to infinity? Okay, well, let's see. So again, this takes about 80 seconds, so it's really pushing my creativity here in filling this void as well. Yeah, maybe to talk a little bit about this countermeasure itself. So double checking this is a common countermeasure. Really, any kind of fault injection, it boils down to detecting that there's a fault, and one of the ways you can do that is redundancy. So you just do things twice or 3 times, and then an attacker can get lucky 1 time, but the idea is that they might not get as lucky 2 times. We are already at 393 faults after 1 minute. All right, let's see who the winners are. So we went down to 393. So it's still a lot, but it's, are you glass half full or half empty person? We actually did knock out a lot of them with, a few lines code chain. So in that sense, it was fairly good ROI. If you plot this, what you'll actually see is that there's still quite a few points in time where you can inject a fault, but we've went down to at a particular clock cycle, only 2 or 1. So where is this coming from? Well, it turns out with fault injection, there's a lot of weird things that can happen. One of the things that we regularly see is that that you jump into, let's say, random looking parts of the code. Now, obviously, there's nothing random at what's going on here. That's what we see when we're doing this in practice. But when we're simulating, we can actually see exactly what happens. One of the examples, I don't have a slide on it, but one of the examples that I've seen is where it actually went into to call into this call, the branch test call. All right, so I was jumping in there, and there was a fault just before that. But it still went into the call, it completed the call, it printed branch test, and then when it returned, it printed success. I'm like, that's weird. Like I'm reading out success way later, so why would a fault at this point actually cause me to print success? And what it turned out is that we were flipping a single bit again, which affected the return address that was being saved by that call. So it made the call, but because the return address was flipped, it returned to some other part of the code. And it turns out that there's a 1-bit difference between returning to this part in the code and returning to the debug print in the code. Now, making countermeasures for that is going to be a little bit harder at the software level because there's actually a lot of these kind of combinations. So, yeah, then you're thinking more about like generic countermeasures like detection circuitries or canaries or other kinds of code flow checks. Like you, for instance, one of the things when you're looking at control flow integrity, not sort of in the, a lot of people know control flow integrity from the exploitation world, where, you know, you're playing around with function pointers and you're going where you're not supposed to go. You can also do that within a function. For instance, I could have a few checkpoints in this code, and I know that if I get to this success play condition, I must have had all these checkpoints. So you can store those in memory, and that makes it harder to glitch again. So there's all kinds of things you can do, but you have to be aware of them first. So let's move on to what you can do at the hardware level. So when we started playing around with the simulation, we of course wanted to have some hardware targets to play around with. And there's this cool project called OpenTitan, which is not Titan M. It's not the security key you were looking at earlier. This is actually a full open source design of a security core. And we were looking into the AES engine specifically, and we were just, as a trial, what we wanted to do is see if we can run AES for one round, which is really bad from a cryptographic perspective. If you run AES for one round, you can basically calculate the key just from the output. So what we did is we took the Verilator code, which you can just, Verilog code, which you can just download off GitHub. This is an open source project. And we calculated what the output would be of an AES given a certain key and a certain input if we would truncate it after, you know, round 1, 2, 3, 4, 5, 6, 7, 8. And now we're just running these simulations, and we're matching them against this table of sort of corrupted AES executions. And then once you get a hit, you can again go and look back and say, oh, I got this hit because I flipped this bit at this point in time. And you can then map that again back to your RTL. So this is just it's a bit of a truncated list of the places that we saw that were vulnerable. And now we're talking about hardware design, so you're seeing these registers here. But there's a couple of ones that sort of stand out, like num rounds, round Q, a couple of bits. So we probably hit the round counter somewhere that caused it to stop. What's interesting about this example is that we did it. So one of the things we saw in the code was this. So if you look at an older version of OpenTitan, which you can do because you have a GitHub history, and you diff it with a newer version, we actually saw at some point a round counter protection had been introduced. So they were actually aware of this problem. So what they did is they had a normal round counter, and they also had a remaining round counter. So one counts up from 1 to 10, and the other one counts from 10 to 1. And what they're actually doing is they're summing them up and checking that that sum is some constant number, namely the number of rounds that you're supposed to execute. Then on top of that, they also had some parity on these things. So there's sort of a double protection going on there. And then finally, somewhere in the state machine, so yeah, there's this, for the people that read Verilog, actually for the people that don't read Verilog, this is an error flag, which once that error sum becomes 1, which means that the counter plus the remaining counter doesn't equal the number of rounds, this flag goes up, and then somewhere in the AES state machine, it basically causes an alert, and it goes into some error condition and should never output any results. So, time for another audience poll. If we had these two GitHub commits, so one before the countermeasure and one after the countermeasure. Let's do percentages this time. So how many fewer fault injection possibilities do you think there were after the countermeasure was introduced? Say 10% less, 0 to 10% less, 10 to 50% less, 50 to 100% less. I can't go over 100. Sorry, that's how percentages work. Sorry?
More is also possible.
More than 100% less vulnerabilities?
More vulnerabilities.
Yeah, you're right. It actually went from 16 to 17. So what happened here? This was really weird, right? There was all this stuff introduced to actually like bolt it down. And it actually made things slightly worse. And I should say slightly because, we're talking about 16 or 17 faults out of the 27, almost 28 million things that we tried. In which case we had a lot of no faults, and other faults are basically ones that we saw corruption on the output, but we couldn't explain it with the round cutting model. There might be other models that could still be exploitable. We just hadn't implemented it at that point yet. So it turns out that you may notice from the software world that if you implement a if statement twice, you have to be really careful because the compiler might optimize it away. In the code that I showed before, I was careful. Guess I can go back to the slide. I was careful because it says volatile here. So volatile tells the compiler, hey, you're going to read at this address. I know you've done it before, but just do it again because it might have changed. So the compiler cannot optimize this second check away. Same stuff happens in so-called synthesis tools. So synthesis tools are the ones that take this RTL and turn it into netlists. You want to make your chip as small and as fast as possible. So any duplication that's in there, better get rid of it. And, counting the round counter twice, which the developer surely must have made a mistake. So let's optimize all that stuff away. And for some reason I don't know why it actually got worse, but it for sure didn't get better because that stuff was just all optimized out. Anyway, we disclosed this to the OpenTitan team. They have a countermeasure now that, we haven't tested it, but they have a countermeasure. So let me go to some final thoughts here. So get your questions ready. How can you learn about these things? So one of the things is I think it's a cool open source project by one of our colleagues. You can download it off the Riskier GitHub. It's a fault injection simulator that sort of only works at the CPU level, not at the hardware level. But you can play around with, trying different countermeasures and seeing why it doesn't work. And it comes with an example of sort of a full secure boot implementation. You can play and try to implement your own countermeasures and see if you can get the number of faults down to 0. I hope Antrix isn't going to kick me out of the conference for this, but I'm going to do a shameless plug. I get a thumbs up again. That's the third one this talk. So Colin O'Flynn and I wrote a book for the past 6 years, unbelievably. So I started when I was young, which covers some of these things. We have a section on countermeasures, but it's mostly about like how do I get into like the field of hardware hacking, all the way from, how does a firmware extraction work to side channel analysis and fault injection and those kind of things. I also want to do another plug for Matt Venn's course. I think he's also in the audience here. Go talk to him about the 0 to ASIC course. Taught me a lot about, everything from Verilog all the way to how a chip is actually made. So I highly recommend that. So some really final thoughts, I promise. So there's some open questions in the work that I've shown you. I guess it does show like, hey, we can simulate some issues before a chip is actually made. We can find both in software and hardware ways to identify issues, fix them and then retry. But it does really still have the open question of how well does this work on actual silicon? We're still using models. I've taken the single bit flip model. Definitely a lot of the fault injections are not single bit flips. So how do you simulate those? We have lots of thoughts on this, but eventually you're going to have to put it in silicon and test. So we're still looking into ways to get chips manufactured and actually do this test. There's performance questions. So you saw on a Pico core, I can do it on my laptop live in front of you, but I cannot do this on a billion transistor chip. right? So what size can we actually still reasonably simulate is a question. And in principle, this stuff scales infinitely. Like you just throw X times more compute power at it, it goes X times faster because I can do all these simulations in parallel. But still, it's interesting to figure out where the sort of limits are within reason. Yeah, finally, and I guess that's more, if I zoom out a little bit further, is that this whole shift left, so really going into like the development space and trying to fix issues there is really important for security, and it's where you can make the most impact. It might not be the most sexy demo, but you know, this is what I think we need to do more as an industry as well to get really to the root of a lot of problems. So yeah, if you want to do this kind of stuff, there's lots of ways to get into the field, either as an amateur or professionally. We always have jobs open, so come talk to me if you're interested in working in this field. And I'll be around today and tomorrow for any questions you have. And that was my really final thought. Thank you.
So do we have any questions?
Hi, Jasper. Thank you for this nice simulation and tooling. It's really nice to see that we are able to model in practice how things can go wrong. Well, I've been doing this for quite a while, as you know, so I think that one of the limitations that we have is imagining and defining success. For example, in the example you provided, the success was being able to print, let's say, or not, secure boot is successful or not. Well, I can think already at least of another way that doesn't fall in this definition but would break secure boot. For example, you know that with instruction corruption, we actually can move the input data to a register. So if you move that to the link register or the equivalent there, as soon as you exit from that function, you would take runtime control.
Yeah.
That will not be caught by your model. So I think that the tool is great, but maybe our imagination maybe should improve.
Yeah. No, it's absolutely correct. So things where sort of the only thing I'm doing here is run the normal code and inject a fault. So what you're saying is, yeah, maybe if we're talking about a secure boot scenario, you know, we've actually given it a corrupted firmware as well, and then we try to, you know, jump into that firmware. In principle, this could be simulated, but you need to prepare that firmware, and it's more work. Yeah. Yeah, thanks. Any other questions?
I'm just curious if you tried to prevent the optimization to actually measure how much protection the double counter is providing.
So you mean in the hardware side or on the software side?
Yeah, on the hardware, yeah, preventing the RTL optimization. Yeah.
So these synthesis tools, they have various ways where you can indicate, like, hey, I think it's like don't touch and keep flags. It then depends a bit on the dialect that the synthesis engine speaks. It doesn't always do what you think. What we've seen, I was talking earlier as well about an example where we saw double flip-flops being implemented. So it was actually a redundancy case where normally, you know, those should always be the same. And the idea is that if you flip one of the two, then an error is raised and you know that you're in a bad state. And that's a good idea. And we really try to keep the second set of flip-flops in, because if you don't do anything, they're just optimized away. And it turns out that, yes, indeed, it was keeping this. So we said, you know, keep the second set, and it did keep the second set. But the values were fed from the first set of flip-flops. So if I glitch this side, I automatically get a glitch in my detection as well. So I'm not a Verilog expert or a synthesis engine expert, but we've seen this sort of game of whack-a-mole where yeah, you think that you're implementing a countermeasure, and you're even thinking that you're doing the right thing in your synthesis engine, and then you go and check, and it's still not doing what you want. So you really have to, I think, again, I'm not an expert of that part, but I think you really have to go post-synthesis and sort of manually make sure everything's there, or maybe there's some magic you can do in Verilog to still, you know, wrestle the synthesis engine to do what you will. But yeah, it's I don't think there's a bulletproof answer to that right now.
Maybe to expand on that previous question, is this a signal to the synthesis tools makers that they need to add better support for this stuff not getting optimized out? And the second question is, you mentioned simulating more complex systems might not be feasible. Can you still take the learnings from a simpler example and apply those to more complex systems?
Yep. So the first question, yeah, and this is sort of the direction I think we are heading. So we work with agencies like DARPA, the U.S. Defense Advanced Research Project Agency, and there you can already see discussions around these EDA tools. They optimize for PPA, what they say, power performance area. Those have been things that are optimized for. And none of those like redundancy, right? So redundancy must go. So we're actually talking now about adding a fourth leg to that, PPAS, to add security to that as well. And these tools just don't have that right now. But ideally, yes, I think you want to start having some sort of levers in your process to add that security part as well. And then to your second question, so can you do small experiments and that will cover you for the greater SOC, I guess? The way we're looking at it right now is that a lot of faults occur at one subsystem or maybe between two subsystems. So you can just pick and choose sort of the subsystems that you want to fault, and then use that as a proxy of how things would be on the full SOC. It's definitely not perfect. We're going to miss things, but it's better than not being able to simulate. So nothing complicated going on there, but open to thoughts.
CERN gave a talk about designing CPUs and ASICs for their high radiation environments, which are basically operating in constant fault injection type worlds. And they also mentioned that they had triple redundant designs where the optimizer had removed two of them and things. Has there been any overlap between the fault injection community and the sort of the high power, high energy physics community in designing these sorts of tools?
Yeah. So there's definitely overlap. Actually, if you look at historically where sort of all the fault injection tools come from are all sort of from the same space of fault tolerance and failure analysis. So once you start shooting chips into space, high radiation, actually your chip is basically constantly being fault injected. So there's things like, TMR, tri-modular redundancy, which is basically like, let's say you make from one flip-flop, you make three, and you have some voting logic that if one flips, the other two are still saving the day, if you will. The main difference is that with the in space, it's sort of Mother Nature is the enemy. And Mother Nature are just like small particles that cause relatively small faults. When you look at what fault injection doing, it's actually blasting a lot more energy at a chip. And also it's doing this in a more or less controlled way. So the more energy actually causes, more than one bit flip. So if I flip 2 bits in a TMR, I still, effectively glitched that thing. So what we see in practice is with any of these kind of redundancy mechanisms that might be borrowed from the, radiation hard community, the success rate goes down of fault injection, but generally not to zero, because of that effect that you might still be lucky enough that you glitch 2 instead of one gate. So yes, there's a lot to learn, but the fact that it's not, or the fact that it's an attacker actually blasting a lot more directed energy makes it not the final solution. See another question.
Great talk. Thank you, Jasper. I was just interested because Verilate is a simulator that's optimized for doing things extremely quickly, but we don't actually do synthesis there. So it seems like an interesting thing that could be cool to explore later would be use a synthesis tool like Yosis, get the gate level netlist, and then simulate the real gates, because you may find a totally different set of vulnerabilities there. And I'd be interested to know what the differences or the commonalities between the Verilator and the gate level simulation would be.
I can give those to you. So actually, I skimmed over this, but what you've seen here is actually a gate level sim that I've done. So we've done Yosis, we've done the synthesis, and then we run it through Verilator. But as you know, that's a lot slower than doing simulations at the RTL level. So we've done sort of an in-between where we did an elaboration of the netlist, and then adding again a glitch bus to that, which runs a lot faster than like the final netlist. And we see and I have to say this was on a small example, a one-time thing, but we saw about a 90% overlap in the results that we saw from pure RTL simulation versus the gate level simulation. So there's a bit of a performance accuracy trade-off there, but it's definitely a good thought, I would say. Yeah.
Okay, I think we've pretty much run out of time. Sorry, we're going into the coffee break now. But yeah, if you want to hook up and chat, don't forget we've got the speed networking, not dating thing going on at the moment.
That's my fault.
So yeah,
it's a lot of fun.
Thank you.